Imagine boarding a commercial aircraft, settling into your seat and looking to your left, only to find a blank wall. No oval frame, no plexiglass, no thin strip of sky. Just a smooth, unbroken panel of composite material where a window used to be. Most passengers would demand to get off the plane. Airlines would never dare. And yet, the windowless fuselage is not science fiction dreamed up by a startup with a PowerPoint deck. It is a concept with serious engineering credentials, documented economic logic, and the backing of some of the sharpest minds in aerospace. The real question is not whether this idea is crazy. The real question is whether the industry already knows it is inevitable and is simply waiting for the world to be ready. To understand why anyone would remove windows from a commercial aircraft, you first have to understand what windows actually cost the industry. Not in dollars, though that number is staggering. In physics, every window cut into a fuselage is a structural wound. The aircraft's skin, typically aluminum alloy or carbon fiber reinforced polymer, is designed to carry load across its entire surface. When you cut a hole, you redistribute that load around the opening. Engineers call this stress concentration, and it is not a small problem. The oval shape of aircraft windows was not chosen for aesthetics. It was chosen because corners concentrate stress catastrophically. Rectangular windows were a fatal lesson learned from the de Havilland Comet, the world's first commercial jetliner, which suffered explosive decompression failures in 1954. Square window corners had propagated metal fatigue cracks at altitude until the fuselage simply tore apart over the Mediterranean. The oval was the fix. But even an oval window requires reinforced frames, additional fasteners, thicker skin panels around the opening, and seal systems that must be inspected, maintained, and eventually replaced. Multiply that across 130 windows on a typical narrowbody, and the structural overhead becomes significant. Then there is the pressurization challenge. An aircraft fuselage at cruise altitude maintains an internal pressure equivalent to roughly 8,000 feet above sea level, while the external environment is closer to 35,000. That differential is roughly 12 pounds of force pressing outward on every square inch of fuselage skin. Every window is a potential leak point. The seals are engineered to extraordinary tolerances, but they degrade. They accumulate frost cycles. They flex with every pressurization cycle. And a typical commercial aircraft completes one pressurization cycle per flight, racking up thousands of cycles over its operational life. Maintenance costs for window seals and frames run into millions of dollars across a fleet's lifetime. Aerodynamically, windows represent yet another compromise. They create surface discontinuities that marginally disrupt laminar airflow, adding what engineers call parasitic drag. The contribution of any single window is almost immeasurably small, but aerodynamicists work in increments. A 1% improvement in drag across a long-range widebody translates to millions of dollars in saved fuel over a decade of operations. Remove all the windows, smooth the fuselage into a continuous surface, and you recover every one of those increments simultaneously. The numbers compound in ways that make airline finance executives sit up very straight. The concept gained serious public attention when the Centre for Process Innovation, a British technology organization backed by government and industry funding, released its windowless aircraft concept in 2014. Their proposal was not to fly passengers in darkness. It was to replace every window with a thin, flexible OLED display panel embedded in the fuselage wall, connected via fiber optic cables to external cameras mounted along the aircraft's skin. The passenger would see a real-time, photorealistic panorama of the outside world, not through a small oval portal, but across an entire wall surface. In business class, you could theoretically have a floor-to-ceiling view of the curvature of the Earth at sunset. In economy, every seat would become a window seat. The experience would be more visually immersive than any conventional window could offer, while the fuselage itself would be stronger, lighter, and cheaper to maintain. The engineering logic is sound. OLED panels have become extraordinarily thin and flexible. Fiber optic transmission of high-definition video is mature technology. The cameras themselves require minimal structural intrusion, a small lens housing flush with the fuselage skin, orders of magnitude simpler to seal and maintain than a full window assembly. The structural gains from eliminating window cutouts would allow engineers to reduce the gauge of surrounding skin panels, saving weight that directly translates to either increased payload capacity or reduced fuel burn. Early estimates from materials researchers suggested potential weight savings in the range of several hundred kilograms per aircraft, meaningful in an industry where airlines pay to carry every kilogram, every flight, every day. The competitive implications run deep. Consider what this means for aircraft manufacturers. Boeing and Airbus spend decades amortizing the tooling and certification costs of existing fuselage designs. A windowless fuselage would require entirely new type certification, a process that costs hundreds of millions of dollars and takes years. But the manufacturer that achieves it first would hold a structural and aerodynamic efficiency advantage that competitors could not quickly replicate. The aircraft would be lighter, more fuel efficient, and operationally cheaper than anything currently flying. For airlines operating on margins measured in fractions of a cent per seat mile, that advantage would be decisive. And yet the obstacles are real. Certification authorities, particularly the FAA and EASA, require redundancy in critical systems. A window, for all its structural complexity, has one overwhelming virtue. It requires no power, no software, no camera, no data connection, and no display driver to show a passenger the outside world. If an OLED panel fails, the passenger sits in a blank-walled tube. If the camera system malfunctions, every display in a fuselage section goes dark. Regulators would require backup systems, redundant power supplies, and fail-safe protocols that would add cost and complexity, potentially eroding the very efficiency gains the concept promises. There is also the question of passenger psychology. Studies on consumer behavior in aviation consistently show that window access influences seat preference and willingness to pay premium fares. Whether passengers would adapt to camera-mediated external views, or whether the absence of a physical window would trigger anxiety, remains genuinely uncertain. The most honest reading of where this technology stands is that it is not blocked by engineering. It is blocked by certification frameworks, consumer psychology, and the brutal economics of aircraft development cycles. Airlines cannot gamble fleet transitions on concepts that may fail regulatory approval. Manufacturers cannot bet their balance sheets on passenger acceptance of a fundamentally alien interior environment. The industry moves conservatively by design, because the consequences of moving incorrectly are measured in lives, not merely in market share. But here is the shift in perspective that changes everything. The windowless fuselage is not primarily a passenger experience concept. It is a structural efficiency concept with a passenger experience wrapper. The deep logic has always been about weight, drag, and maintenance cost. The OLED panorama is the solution to the only real objection, that people need to see outside, not the core proposition. And as composite materials mature, as OLED technology becomes cheaper and more reliable, as certification frameworks evolve to accommodate digital redundancy rather than physical analog backups, the engineering case grows stronger with every passing year. Aviation history is full of ideas that seemed absurd until the moment they became obvious. Turbofan engines were once considered grotesquely oversized compared to the sleek turbojets they replaced. The fly-by-wire system that digitally mediates every control input on a modern Airbus was deeply controversial before it became the industry standard. The windowless fuselage sits in precisely that waiting room, technically coherent, economically compelling, and culturally premature. The window is not a feature. It has always been a compromise. And the day that compromise is no longer necessary, the sky will look very different from the inside of an airplane.